Okay, continuing with step growth polymers or polymerization, you can use diols to do an addition reaction to cyanates. Okay, so this is a cyanate. Cyanate is this group. You can attack. Okay, you know this carbon right here, because of dipole moment, the carbon is partially positive, so you can attack or add the alcohol to that carbon, and the pi bond will open up. Okay, so the pi bond will open up. In this case, most likely it was the nitrogen because of the benzene ring, so it will open up, and as it open up, it's gonna pick up a proton. So you can imagine that you're going to have an amide formed. Okay, you can imagine you can have an amide formed, because as nitrogen picks up the hydrogen, you get NH, and of course that hydrogen that's picked up is this extra hydrogen from the alcohol. So this oxygen here can do the same thing, attacking another cyanate. Okay, so let me just say this is an aryl group meaning it's another monomer, so you can attack here and this opens up. Okay, opens up picking a proton, which is this proton right here. So doing so, you get another monomer attached to this end, or it could be an attack of another diol onto this cyanate. You get this group right here. Okay, so this looks like an amide, but because you have an oxygen there, it's no longer an amide. Okay, it's no longer an amide because of the oxygen. Okay, so that you will have added the alcohol piece. This is the diol piece that's added onto the cyanate. This is the alcohol piece that's added onto the cyanate. It looks complex, but it happens. So in summary, if you have a cyanate, let me give you a summary here so you don't get confused. If you have a cyanate and you add an alcohol, okay, let's use a different color. Let's say you have an alcohol. So basically, the oxygen attacks the carbon, the nitrogen steals the hydrogen. That's the shortcut. Okay. In fact, the best way to show it, yeah, it's like that, and then this bond goes to the oxygen. So if you do this short, it's not the right mechanism, but it's just a shortcut to quickly predict the product. So you'll have this carbon bonded onto the blue oxygen. Okay, the nitrogen picked up the blue hydrogen, and of course this is the R group. The R group could be the rest of the structure. So now let's show this oxygen bound to the carbon, and then we show they are bound to the oxygen, and then we show that this nitrogen took the blue hydrogen. Again, you're making this functional, which is that. Okay, so this type of functional group is called a carbamate. So polymers that are made in this way, using this method, are called polycarbamates. They are not amides, they are carbamates, and the general functional group is what looks like an amide, but you'll have an oxygen too. So this is the carbamate. Okay, this functional group here, NH carbonyl oxygen, that's a carbamate. And I've given you the shortcut on how to see it. So it can happen here or down here. Remember, we said step growth polymers are made from difunctional. They are made from difunctional monomers. So you can make your carbamate right there, which contains an amide in it, but because of the oxygen is called a carbamate. Or you can have a carbamate down here, and then because the alcohol is a diol, the other OH can create another carbamate to another monomer of the dicyanate, and so on and so on. Carbamates are used to make adhesives. Okay, so you produce a liquid polymer commonly used as varnish or wood products. Varnish in itself is an adhesive. Okay. The introduction of water, however, will produce a foam commonly used as insulation and packaging. You get a foam. So if this is your cyanate and you're adding water, remember what we said, whatever an alcohol can do, like we did here, the alcohol adding to the cyanate to produce the carbamate, whatever an alcohol can do, the water can do, and vice versa. So I'll still use the same shortcut where the oxygen will attack the carbon of the cyanate, and this nitrogen will receive the hydrogen of the water, and of course we give back the lone pair that was used up there to this oxygen. Okay, so if you do so, then this blue hydrogen ends up onto the nitrogen. Okay, if I were to show it, it's right there, and then the blue OH is attached to the carbon or the carbonyl. So basically you've added the H to the nitrogen and the OH to the carbon of the carbonyl of the cyanate. So you end up with, see, you have a carboxylic acid form, but you're gonna call it a carbamic acid. Carbamic acid, it's no longer carbamate, it's a carbamic acid, and the carbamic acid can scramble. How do I show that? There's another mechanistic shortcut for this. So this nitrogen would accept that hydrogen, okay, and then the bond between oxygen and hydrogen will be resonated inwards, and then this bond will break towards the nitrogen. So notice that you're cleaving this section. At the same time, you're losing the hydrogen to the nitrogen. So the nitrogen becomes NH2. Okay? It had one hydrogen, it took one more, the blue one. So you get NH2. And then here you're making a double bond as you lose the other bond. So basically this would have been the structure, but the geometry is wrong. It's supposed to be like this. That happens to be CO2. that's lost. Okay, so you get an amine, primarily a primary amine. So the CO2 produces small bubbles, and this results in a foam rather than a liquid. So whenever you do hydrolysis, uh, of cyanides, you get a foam, all because of the CO2 that creates bubbles, which helps in insulation and packaging. Okay, so if it's a polymer, you get a foam, something that's spongy, that can be used to package your delicate um, things that you bought. Alright, so we talked about thermoplastic polymers, and we said if you heat such polymers, they deform or they lose shape, but if you cool them, they reform or regain their shape or physical properties. Those are thermoplastic polymers. Thermosetting plastics, uh, they form additional links when heated, which result in the loss of a small molecule, and this reaction is irreversible. Thermoplastics are reversible, thermosets are irreversible. For example, bakelite. The bakelite is made from a phenol and an aldehyde. When we talked about aldehydes and ketones, we said that alcohols can add onto aldehydes. Okay, so you get a cross-linked dipolymer which is very rigid. The cross-linking helps the dipolymer to be rigid. Actually, this is a plastic. The plastic is highly resistant to heat. Okay, so it's used for insulation, and it's tough. Can also be used to insulate your handles of your cooking pans. So in the kitchen where you have your cooking pans, this handle can be covered by bakelite. Why? Because bakelite plastic is resistant to heat, so you can use it for insulation so you don't get burnt up. Okay, back to our reaction. So in this reaction, you are going to combine. So let's focus on what's happening here, then we'll know who is lost. So going across, there are two shortcuts I can show you here. So if you are adding an aldehyde, okay, which is having a CH, that's an aldehyde. So the shortcut is to lose a small molecule. In this case, the small molecule obviously will be water molecules. Okay, so if you are combining two phenols, so now we are focusing on how this was formed, probably by using our little shortcut because we are avoiding too much mechanisms for this class. So you will have those two hydrogens. See, there's no hydrogen here, there's no hydrogen there, so where did they go? They were lost. Those two hydrogens and the oxygen will be lost. What does that give you? It gives you H2O. When that happens, you just joined your two phenols using a CH2, but the two phenols have sacrificed their OHs. So now in the middle, I have to show my CH2 that's joined. That's joining the two rings. So that's a CH2, that's a CH2, that's a CH2, and so forth and so forth. Okay, now that's going across. Okay, going down is the same thing. Okay, going down is the same shortcut you can use to see how bakelite is formed. So you have a hydrogen you have a hydrogen, okay, and then you still have your CH, you have your aldehyde, so to speak. You have your aldehyde and you have your oxygen, and then you still have your phenol. So you have your phenol, I don't know where I'll put it. Let me just squeeze it somewhere here. Okay, that's your phenol. Okay, that's our little phenol. But this time we are using the ortho hydrogen of this. Okay, so we use the ortho hydrogens here. So we're still using the ortho hydrogen, but our ring is kind of rotated. So again, our shortcut will dictate that we lose the oxygen and the two hydrogens. Again, you're losing water. So this CH2 that's left will be clicked to the two rings, and it's this CH2, and it's gonna be that CH2. It's gonna be this CH2, gonna be that CH2, as explained up there. So you see, you're joining the phenol rings together. Each time you join them, you're losing a water. You're left with a CH2, which is this blue part here. That's the blue part there. That's giving you the CH2s with this shortcut. So you get perchlorate, which is strong and is used for insulation. The reaction is thermosetting. You cannot go back to get its physical property once you make it. Okay. Another important thermostatic plastic is urea formaldehyde. This is another plastic, and I will still tell you that you're gonna lose water. So you see how we are making CH2? All those are CH2. So which means the oxygen was somehow lost. Okay. So if you were to focus on this place right there, okay, it means the two hydrogens and the oxygen will make water. Okay, so you will have CH2 here, you will have CH2 there. As you lose water, that's what this means. So the same thing will happen on the other side. You lose water. Okay, so you are using your CH2 to link up the amides. We shall talk about the final important class of stable polymerization, which are epoxy resin, next time in the video.